Beneath the widest sky on Earth lies a body of water so immense that it reshapes the planet simply by existing. From horizon to horizon, it stretches beyond sight, holding more water than all continents hold land, pressing its weight against the crust of the world itself. There are trenches within it, deeper than mountains are tall, pressures strong enough to crush steel, and ecosystems that survive without a single ray of sunlight. And in that vast expanse, every descent has revealed something no one expected to find. The Pacific Ocean covers more than 63 million square miles, larger than all the land on Earth combined, and holding more than half of the planet's free water. Its average depth sinks beyond the height of most mountains, and nearly 7 miles below the surface lies the deepest known point on Earth, where pressure rises more than 1,000 times stronger than its sea level. More than 80% of its floor remains unmapped in detail. We have better charts of Mars than of the world beneath these waves. Beneath that immense surface, entire mountain ranges stretch longer than the Rockies, and tectonic plates grind along the Ring of Fire, forming trenches where continents slowly descend. Near freezing waters exist beside vents hot enough to melt metal. In the blackness below sunlight, ecosystems survive without the sun at all, feeding instead on chemical energy rising from the planet's interior. Scientists once believed such life was impossible. The ocean answered otherwise. Strange sounds have echoed through these depths, recordings that took years to explain. Cameras lowered into trenches have revealed organisms living under crushing pressure, their bodies softer, their proteins adapted to conditions that would destroy familiar life. Some glow, some live for centuries. New species are documented each year, and every expedition has returned with something unexpected. But how much of this ocean remains unseen even now? What forms of life continue to endure where no human eyes have ever looked? How did organisms learn to survive without sunlight, under pressures that could shatter steel? And what discoveries have already forced scientists to reconsider what life can endure? Tonight, we descend through documented discoveries, following the evidence left behind by cameras, instruments, and patient observation. But before we begin, I would love to know where in the world you're listening from and what the time is there. It is always fascinating to think of these stories being heard across so many different skies. If you enjoy these gentle journeys into Earth's mysteries, please do consider leaving a like and subscribing to the channel. So now take a deep breath, let your shoulders loosen, and together, let us descend into the deepest parts of the Pacific. Long before waves traced their shifting paths across its surface, the basin itself was being assembled in silence. The ground beneath the water was never still, though its motion unfolded at a pace too gradual for any tide to reveal. Vast slabs of Earth's outer shell drifted across the planet's mantle, gliding only a few inches each year, yet carrying entire continents and seafloors with them. Over spans of millions of years, those patient movements arranged the immense hollow that would cradle the Pacific, shaping its boundaries with the quiet persistence of stone sliding over stone. These slabs, known to geology as tectonic plates, meet along seams that form a restless ring encircling much of this ocean. Along that perimeter, plates converge, and one edge bends downward, slipping beneath another into the mantle below. This descending motion is called subduction, though in the language of the planet, it resembles a slow exhale, crust folding back into the interior from which it once rose. The chain of these boundaries is often called the Ring of Fire, not for constant flames, but for the arcs of volcanoes and tremors that mark where the crust returns to depth. Islands lift there, mountains gather there, and the outline of the ocean itself is refined through that steady exchange. The Pacific grew deeper than its neighboring oceans, largely because of its age and its edges. Much of its floor formed long ago at spreading ridges that pushed new crust outward, giving it time to cool, thicken, and sink slightly as it aged. Around its margins, the continual descent of plates pulls the seafloor downward into elongated depressions. These are the trenches, narrow and immense, shaped where one plate slides beneath another and draws the surface into a downward curve. Rather than a single cavity, the basin is a mosaic of such features, each one a record of motion written in stone. Depth alters everything that settles within it. As the seafloor sinks, water gathers above in greater volume, pressing more firmly, cooling more completely, dimming more thoroughly. Minerals dissolve differently, currents travel along unseen contours, and chemical gradients form where rock and water meet. In these lower regions, matter behaves according to rules set by weight and temperature rather than wind or sunlight. The architecture of the basin guides those conditions, determining where ridges rise, where plains extend, and where fissures open to release the planet's inner heat. Through this slow construction, the ocean became not only the widest, but also the most profound of Earth's waters, its shape molded by forces older than any shoreline. The groundwork now lies complete, the immense stage prepared by drifting plates and descending crust, ready for the remarkable inhabitants and phenomena that have taken form within its depths. On certain nautical charts, there is a narrow crescent in the western Pacific where contour lines gather so tightly that they nearly merge, as if the map itself hesitates to follow them farther. This arc marks the Mariana Trench, a long indentation east of the Mariana Islands, its length stretching for thousands of miles, while its width remains slender, a seam pressed into the planet's outer skin. Within that seam lies a smaller hollow known as Challenger Deep, the lowest surveyed point on Earth, where measurements descend to about 36,000 feet below the surface, a depth so great that familiar scales lose their meaning and distance becomes an abstract notion rather than a traveled span. Reaching that depth required patience measured in decades. Early echo-sounding instruments first traced its outline in the 20th century, their signals returning after long pauses that hinted at extraordinary distance. In 1960, a Bathurst cafe named Trieste carried two observers downward into that remote hollow, its steel sphere suspended beneath a float filled with gasoline for buoyancy. The descent lasted hours, the craft settling slowly through layer after layer of darkening water until at last it rested upon the sea floor. Silt stirred gently beneath it, drifting like pale smoke in the beam of an exterior light. No violent motion greeted them, only stillness and fine sediment shifting in the current of their arrival. For many years afterward, the trench remained mostly untouched, visited only by instruments lowered on cables or autonomous vehicles guided from ships far above. Cameras eventually followed, their housings built to endure the immense weight of water pressing from all sides. When those lenses first transmitted images from the bottom, they revealed a landscape not jagged, as once imagined, but soft and muted, shaped by deposits that had settled grain by grain over uncounted centuries. Tracks crossed portions of the sediment, delicate grooves that suggested passing creatures, though none had yet been seen moving. Later expeditions brought clearer recordings. Small forms appeared within the frame, translucent bodies drifting just above the seafloor, crustaceans pacing slowly across the fine surface, fish with gentle contours gliding through the dim field of view. Their presence altered scientific expectation, since earlier theory had proposed that such depths might be too extreme to support complex organisms. Yet there they were, living quietly, where instruments had once predicted only mineral and water. Submersibles have since returned, some carrying explorers, others guided remotely, each descent adding detail to the portrait of that hidden basin. Lights sweep across ripples in the sediment, revealing subtle slopes and scattered stones, while sensors note temperature, chemistry, and pressure with steady precision. The trench remains remote and seldom visited, yet its deepest hollow rests there continuously, unchanged by observation, holding its position at the farthest reach of the ocean's downward reach, a place defined not by emptiness, but by the quiet persistence of life at the very floor of the world's waters. In laboratories far from shore, preserved specimens rest within clear vessels, their forms delicate and unassuming, as though they had drifted in from a gentler sea. Labels record the depths where they were collected, numbers descending into ranges once thought unreachable for complex life. Among them are snailfish, pale and supple, their bodies shaped more like drifting petals than the firm outlines of coastal species. When first brought to the surface by specialized traps, they appeared almost unfinished, their tissues yielding easily to motion, their skeletons light and flexible, built not for rigidity, but for balance with an immense surrounding weight. Far below the reach of ordinary nets, cameras have also recorded amphipods moving across the seafloor at depths exceeding 30,000 feet. These small crustaceans resemble translucent commas, their curved bodies gliding with quiet steadiness as they search for particles descending from distant waters above. Their presence reveals a pattern repeated throughout the deepest regions, where life favors softness over armor, subtle chemistry over strength. Hard structures that serve shallow species so well become liabilities under such pressure, while pliant tissues endure by allowing the surrounding force to pass through them rather than resist it. Inside these organisms, survival depends upon molecular architecture as much as anatomy. Proteins, the folded structures that guide nearly every process within a living cell, are subtly altered in deep-dwelling species. Their shapes remain stable even when compressed by the immense weight of the water column, assisted by compounds known as piezolites that stabilize their form. These molecules drift through cellular fluid like quiet attendants, preventing distortion and allowing metabolism to proceed at an unhurried, reliable pace. Without such adaptations, the machinery of life would falter, its delicate geometry pressed out of alignment. The softness of deep fish follows the same principle. Muscles contain more fluid and less dense fiber, bones hold reduced mineral content, and internal spaces lack the gas-filled cavities common in surface species. Gas would contract severely under pressure, so these creatures rely instead on tissues that neither collapse nor expand dramatically. Their bodies exist in equilibrium with their surroundings, shaped by a world where compression is constant and unchanging. For this reason, nothing bursts or implodes in those depths. The creatures that belong there are composed in harmony with the force around them, their internal pressure matching that of the water beyond their skin. Trouble arises only when they are brought upward, when the steady balance that sustained them is replaced by rapid release. Within their native realm, however, they move with gentle certainty, each motion suited to conditions that have remained stable for ages. In that quiet equilibrium, life continues without strain, shaped not in defiance of pressure but in calm agreement with it. There are places in the ocean where warmth rises from stone, not from sunlight above, but from the planet's own interior, seeping through cracks in the crust as if the earth were quietly breathing. Along certain volcanic ridges of the Pacific seafloor, mineral-rich water escapes from fissures and billows upward in cloudy plumes. These openings are known as hydrothermal vents, and when they were first observed in the late 20th century, they appeared like chimneys sculpted from dark minerals, their surfaces layered by particles that cooled and settled as the hot fluid met the surrounding sea. Around those mineral towers, life gathers in unexpected abundance. Pale crabs move slowly over the rock, shrimp cluster in shifting veils, and among them rise the slender forms of tube worms, some longer than a human arm. They stand upright in clusters, their scarlet plumes extending into the water like soft banners. These creatures possess no mouths and no digestive tracts, yet they flourish. Inside their tissues live dense communities of bacteria that transform vent chemicals into nourishment. The worms provide shelter and access to the rising fluids, and in return, the microbes share the energy they create, sustaining the bodies that host them. This process is called chemosynthesis. Instead of drawing power from light, as plants and algae do near the surface, these bacteria rely on substances such as hydrogen sulfide dissolved in the vent water. Through intricate biochemical pathways, they convert those molecules into usable energy, forming organic material in darkness. The principle is simple, though its chemistry is subtle. Life built not on sunlight, but on reactions between water, rock, and heat from below. Entire ecosystems depend on this exchange, each organism linked to the quiet industry of microscopic partners. When these communities were first documented, biological understanding shifted gently yet profoundly. Until then, most theories assumed that sunlight was the ultimate source of energy for nearly all living systems. The vent habitats revealed another possibility, one in which life could arise and persist in isolation from the sky, anchored instead to the planet's inner warmth. It suggested that the conditions required for living processes might be broader than once believed, extending into realms previously dismissed as barren. Such environments also resemble places beyond Earth, where oceans may lie hidden beneath icy crusts. If chemical energy and liquid water can sustain organisms here, then distant worlds with similar ingredients might host their own quiet ecologies. The vents continue to release their mineral clouds in steady rhythm, and around them the tube worms sway gently, nourished by reactions older than sunlight-driven food webs, living testaments to a form of life that draws its strength from the deep interior of a restless world. Far below the routes of ships and the reach of storms, the crust sometimes parts and releases a slow unfolding of fire. These eruptions do not resemble those on land, with ash-filled skies or flowing rivers of flame. Here, the molten rock meets seawater at once, and the encounter reshapes both. Basalt emerges in glowing folds, its surface chilling instantly as it touches the cold surroundings, forming rounded masses that stack gently upon one another. Over time, these shapes accumulate into formations known as pillow lava, each one resembling a softened cushion, its outer skin hardened while its interior once moved with liquid grace. When such an eruption begins, it may pass unnoticed at the surface. The ocean above is vast, and the activity occurs miles below, concealed beneath layers of water that muffle vibration and absorb light. Instruments anchored to the seafloor sometimes record the tremor of shifting rock or the faint acoustic signature of magma breaking through, yet human eyes rarely witness the moment itself. Most discoveries happen afterward, when research vessels return to familiar sites and find that the terrain has changed. Fresh stone spread across the ground where older formations once lay. Newly formed lava carries heat that lingers long after the eruption subsides. As it cools, minerals within the rock interact with seawater, releasing compounds that drift outward in faint clouds. These chemicals become the foundation for living communities that assemble with quiet speed. Microorganisms arrive first, settling upon the dark surfaces and drawing energy from the reactions between water and mineral. Soon, small animals follow, grazing along the thin films of microbial growth. Over months and years, the bare rock hosts more inhabitants, each generation adding subtle motion to what began as silent stone. This cycle of renewal repeats wherever submarine volcanoes awaken. A region that once supported thriving life may be buried beneath fresh lava, its former residents displaced or lost, yet the same forces that cleared the ground also prepare it for return. The ocean does not rush this process. Colonization unfolds gradually, guided by currents that carry larvae and spores across great distances until they encounter suitable ground. The result is a shifting mosaic of habitats, some newly formed, others ancient, all shaped by the steady rhythm of eruptions and cooling. Direct observation remains rare because of distance, depth, and the unpredictability of volcanic timing. Monitoring equipment must endure corrosive water, immense weight, and long intervals of silence between events. Even so, each recorded eruption adds a fragment to understanding, revealing how the seafloor renews itself through cycles of melting and solidifying. In those hidden regions, stone continues to emerge from within the planet, spreading slowly across the seabed, then resting as it cools, becoming the quiet foundation for future life. Along a rocky slope in the Pacific, a small octopus once settled over a cluster of pale eggs and remained there through the passing of seasons that it could not see. The water around her moved in slow currents, carrying faint traces of minerals and distant life, yet she did not leave her place. Her arms curved gently around the fragile spheres, holding them against the stone as though anchoring them to the quiet surface. This still vigil would continue not for days or weeks, but for years, a span far longer than anyone had expected a creature of her kind to endure. The species belongs to a group often called deep-sea octopuses, animals adapted to cold, stable waters where change arrives gradually. Their bodies function at an unhurried pace, each movement measured, each process extended by temperature and depth. Metabolism slows in such conditions, allowing tissues to persist with minimal energy. The brooding mother survives by conserving rather than seeking, her breathing steady, her skin shifting subtly in tone as she blends with the surrounding rock. She does not hunt during this time, relying instead on reserves stored within her body before the eggs were laid. Researchers first encountered this prolonged guardianship while surveying a submarine ridge. Cameras placed near the sea floor recorded the same individual, returning in frame again and again across successive visits. At first, the duration seemed impossible, as most shallow water octopuses guard their eggs for only a few months. Continued observation revealed that this mother remained with her brood for more than 4 years, making her vigil the longest egg-tending period known among animals. Throughout that time, the embryos developed slowly, nourished by yolk within each capsule, their growth synchronized with the steady rhythm of their environment. Such patience reflects the conditions in which these animals live. In cold depths, development proceeds gradually, and longer brooding offers protection against disturbance. The mother's presence shields the eggs from drifting particles and small predators, her arms gently clearing debris that settles upon their surface. Her stillness becomes a form of care, an unbroken watch maintained through the slow passage of time, measured not by daylight, but by the silent progression of internal change. When the young finally emerge, they drift away as miniature versions of their parent, prepared from the moment of hatching to inhabit the same calm surroundings. The mother's task ends then, her strength nearly spent, her long vigil complete. The discovery of such endurance reshaped scientific understanding of how life can adapt its rhythms to match the pace of its world. In that quiet corner of the ocean, devotion unfolds without haste, guided by patience measured in years rather than moments. a gentle testament to the ways living beings align themselves with the tempo of the earth itself. Old maritime journals once carried careful sketches of enormous tentacles and unblinking eyes, drawn by lamplight from the accounts of sailors who had glimpsed something vast moving beneath their vessels. For generations, such descriptions drifted between science and legend, their details debated in lecture halls and chart rooms alike. The creature they described, later named the giant squid, remained known mostly through fragments, beaks found in whale stomachs, pale remains tangled in fishing lines, or bodies washed ashore after storms. No one had watched one alive in its own realm, and so its true nature lingered like an unfinished sentence in the record of ocean life. That absence changed in the early years of the 21st century when a deep-sea research team lowered a specialized camera system into waters far from land. The device carried bait and soft lights, designed not to startle passing animals. For hours, the lens recorded only drifting particles and faint currents, until at last a shape entered the frame, long arms unfolding with deliberate grace. The animal's body shone faintly, its skin reflecting the limited illumination like satin moving through shadow. It did not thrash or dart, as earlier tales had suggested. Instead, it approached with composure, extending two elongated feeding tentacles toward the bait in a motion both precise and unhurried. Later expeditions captured clearer footage, revealing details never before witnessed. The eyes were immense, among the largest in the animal kingdom, suited for detecting the slightest glimmer in dim surroundings. Fins at the rear of the mantle pulsed gently, guiding the animal forward with measured strokes. When it grasped an object, the suckers lining its arms rotated subtly, testing texture through touch as much as through sight. Each movement suggested an organism adapted not for frenzy, but for patience, attuned to a world where energy is conserved and gestures are deliberate. Even now, these squid remain seldom seen. Their habitat lies far below ordinary observation routes, and they appear to travel alone rather than in groups. Their bodies are delicate, easily damaged during capture, which explains why earlier specimens reached the surface in poor condition. Modern encounters rely on quiet technology and long waiting, allowing the animal to reveal itself without disturbance. Through such glimpses, understanding has shifted from myth toward familiarity, though never toward complete certainty. In the recorded sequences, the giant squid drifts beyond the edge of the frame as calmly as it arrived, its form dissolving into the surrounding dimness until only open water remains. The camera continues its watch, lens steady, while the creature resumes its silent passage through the immense and hidden distances it calls home. Light appears in the deep ocean in places where no sunrise has ever reached, kindled not from above but from within, living bodies themselves. It flickers along passing forms, pulses in brief signals, or glows steadily like a lantern carried through an unseen corridor. This illumination is called bioluminescence, a natural process in which specialized cells produce light through chemical reaction. Within those cells, molecules known as luciferins release energy when they interact with oxygen, guided by enzymes that control the timing and intensity of each glow. The result is radiance without heat, a quiet shining shaped entirely by living tissue. Across the Pacific depths, countless species carry this ability. Some bear rows of tiny organs along their sides, each one capable of emitting a measured flash. Others hold luminous bacteria within transparent chambers, allowing microbial partners to provide their glow. The patterns differ from one creature to another, forming arrangements as distinctive as fingerprints. In darkness so complete that shape dissolves into absence, these signals become a language written in light, brief pulses conveying presence, identity, or readiness to reproduce. A sequence of flickers may announce a companion, while another rhythm may warn that the bearer is not easily taken. Many animals use this inner light to soften their outline. From below, a predator searching upward might detect the faint brightness of distant waters far above. To avoid appearing as a silhouette against that dim glow, certain fish and squid produce light along their undersides, matching the tone of the faint radiance overhead. This method is known as counter-illumination. By adjusting brightness to mirror the environment, they dissolve into the background, their forms blending so precisely that their passage leaves no visible trace. Elsewhere, sudden bursts of brilliance serve as distraction. A shrimp may release a cloud of luminous fluid, a drifting veil that glows while the animal slips away. Some jelly-like drifters send waves of light rippling across their bodies, each pulse traveling like a slow heartbeat along transparent tissue. These displays last only moments, yet in that brief interval, they can redirect attention, confuse pursuit, or startle an approaching hunter long enough for escape. The prevalence of such living light suggests that darkness is not empty, but filled with signals too subtle for distant observers to notice. Each flash is brief, each glow small, yet together they form a shifting constellation that never appears on any surface chart. In those hidden expanses, brightness belongs not to the sky but to the inhabitants themselves, and the ocean's quiet depths shimmer with countless private stars, each one born, shining, and fading within the gentle rhythm of life far below. The footage arrived not as spectacle but as a quiet sequence of drifting images recorded by a remotely operated vehicle exploring a trench slope nearly 7 miles beneath the surface. At first, the scene appeared almost empty, a pale expanse of sediment stretching beyond the frame. Then a small figure entered from the edge, moving with gentle motions that stirred faint trails behind it. This was the Mariana snailfish, the deepest dwelling fish yet documented, observed at depths exceeding 26,000 feet, where few vertebrates were once expected to persist. Its form seemed delicate, almost translucent, the body tapering softly toward a thin tail. Unlike coastal fish whose muscles hold firm contours, this species appeared lightly assembled, its structure shaped more by fluid than by rigid support. The skeleton contains reduced mineralization, and the tissues hold a gelatinous consistency that allows the surrounding pressure to pass through rather than press inward. Such softness is not weakness, but adaptation, a design suited to conditions where solidity would invite strain. The animal's movements reflected this balance, each motion smooth and unhurried, as though guided by the water itself. Within its cells, specialized molecules help maintain stability under immense weight. Compounds known as osmolytes accumulate in the tissues, reinforcing proteins so they retain their functional shapes. Without these chemical companions, the intricate folding of those proteins would distort and essential processes would falter. Instead, the snailfish continues its quiet existence, its internal chemistry tuned to the environment with remarkable precision. Even its skin contributes, lacking heavy scales and remaining thin enough to equalize pressure without resistance. The camera's lights illuminated the animal only briefly. It did not startle or dart away, but drifted calmly across the frame, adjusting its fins in small strokes that guided it along the seafloor. Its dark eyes faced forward, attuned to subtle cues rather than bright images. No elaborate coloration marked its body, only a faint translucence that blended with the muted surroundings. In that still moment, the fish seemed less like an intruder and more like a natural extension of its setting, a living presence shaped by conditions that define every aspect of its form. Researchers who reviewed the recording recognized the significance at once. Vertebrate life had been confirmed at a depth once thought beyond its reach, demonstrating that the limits of survival extend farther than earlier estimates suggested. The snailfish did not appear burdened by its environment. It moved with quiet certainty, its body aligned with the forces around it, sustained by chemistry and structure refined through generations. As the vehicle continued its survey, the small figure receded into the pale distance until it blended with the faint textures of the seabed. Nothing dramatic marked its departure. The record remained in the captured frames, a gentle testament to endurance in one of the most remote habitats known, where even the lightest movement becomes part of the slow and patient rhythm of the deep. In certain hidden depressions of the Pacific seafloor, the water gathers into shapes that resemble quiet ponds, their surfaces smooth and clearly defined against the surrounding sea. These formations are known as brine pools, though they are not separate from the ocean so much as denser layers resting within it. The liquid inside them contains such high concentrations of dissolved salts and minerals that it becomes heavier than the water around it, settling into hollows like clear glass poured into stone basins. Their edges appear almost outlined, a wavering boundary where two kinds of seawater meet yet do not readily mix. The origin of these pools lies in ancient deposits buried beneath the seabed. Over long intervals, subterranean salt layers dissolve into groundwater and rise through cracks, emerging onto the ocean floor as concentrated streams. As this mineral-rich fluid spreads, it forms lakes whose salinity can exceed that of ordinary seawater several times over. The density difference prevents immediate blending, allowing the pools to persist as distinct bodies, their surfaces rippling faintly when currents pass above. Light from submersibles often reflects sharply off these boundaries, giving the impression of a shoreline even though all is submerged. Within the brine itself, conditions prove inhospitable for most animals. The concentrated salts disrupt cellular balance, drawing moisture outward and interfering with essential biological processes. Oxygen levels inside the pools remain extremely low, and certain dissolved compounds can be toxic. For many organisms, crossing that boundary would be like entering an atmosphere unsuited to breathing. As a result, the interiors often remain nearly empty of visible life, their stillness unbroken except for slow chemical shifts. Yet, along the margins, where dense brine meets ordinary seawater, life gathers with quiet persistence. Mussels cluster there, their shells slightly open as they filter the surrounding currents. Shrimp and small fish hover just beyond the boundary, navigating carefully as though aware of an unseen threshold. Microbial mats spread across nearby sediment, their colors faintly iridescent under artificial light, nourished by chemical gradients created where the two waters touch. These edges provide both resources and refuge, a narrow band where conditions allow survival. The contrast between the pool and its surroundings creates a layered world within a single landscape. A gentle slope may lead from ordinary seabed into a basin filled with fluid that moves differently, refracting light and distorting shapes beneath its surface. Instruments lowered into such a pool register sudden shifts in density and chemistry, confirming what the eye perceives as a subtle yet decisive transition. Each pool becomes a contained environment, shaped by geology and maintained by the quiet physics of salt and water. They remain scattered across the Pacific floor, rarely encountered and seldom disturbed. Their surfaces lie still within the larger sea, holding their concentrated depths in patient balance, while around their edges, small communities continue their measured lives beside these secluded underwater lakes. Long before any camera descended into the far reaches of the Pacific, instruments were already listening. Suspended in the water or anchored to the seafloor, hydrophones received vibrations that traveled through the vast body of the ocean with remarkable clarity. Sound moves through seawater faster than through air and with less loss of strength, so a single distant noise can glide for hundreds or even thousands of miles. In that unseen acoustic landscape, the ocean carries whispers, pulses, and long rolling tones that pass through darkness like slow currents. Among the most widely discussed of these recordings was a signal detected in 1997 by monitoring equipment spread across the Pacific. The sound rose suddenly, deep and powerful, then faded, lasting only a minute, yet spanning frequencies unlike most known sources. It became informally known as the bloop, a name soft enough to match its strange brevity. At first, its origin remained uncertain, though later analysis suggested that it resembled natural ice activity rather than any living creature. In remote polar regions, vast sheets of ice sometimes fracture or grind against one another, releasing resonant vibrations that travel through the ocean's layers until they reach distant sensors. These events, often called ice quakes, form part of the hidden soundtrack of the sea, their tones shaped by pressure, temperature, and shifting frozen mass. Not all underwater sounds arise from geology or ice. Many belong to animals whose lives unfold far from sight. Whales, for instance, send calls across immense distances, their voices traveling through water with a steadiness impossible in air. Some species produce low-frequency notes that can cross entire ocean basins, linking individuals separated by horizons and currents. These vocalizations vary in pattern and duration, sometimes forming sequences that repeat with subtle variation, like phrases spoken in a language carried entirely by vibration. Hydrophones capture these calls as undulating lines of sound, each contour reflecting breath, muscle, and intention. The ocean's ability to transmit sound so effectively comes from its density and elasticity. Water molecules sit closer together than those in air, allowing vibrations to pass from one to the next with minimal loss. Temperature layers and salinity gradients can bend these waves, guiding them along natural channels where they travel even farther. In certain depths, sound becomes trapped between layers, moving outward in all directions while remaining confined within a narrow vertical band. Within these acoustic pathways, a signal may journey for extraordinary distances before dissolving into silence. Listening devices continue their patient work, recording the shifting chorus of natural signals that pass through the Pacific. Some are brief, others extend for hours, yet each belongs to a living or moving source somewhere beyond view. The ocean remains filled with voices that travel without interruption, their tones drifting across unseen expanses, composing a quiet symphony that unfolds whether or not anyone is there to hear it. Far out in the Pacific, when a whale's long life reaches its quiet end, its body begins a final descent through open water, moving slowly downward through layers unseen. Gravity guides this passage without haste, and as the great form sinks, smaller fish accompany it for a time, drawn by the faint signals of change. Eventually, the body settles upon the seafloor, coming to rest in stillness, its presence marking the beginning of an ecological transformation that unfolds in patient stages. At first, mobile scavengers arrive. Sleeper sharks, hagfish, and other roaming feeders detect the fallen giant and gather around it, their movements steady as they remove soft tissue. This phase can last months, the large visitors gradually reducing what once powered immense migrations to scattered fragments. Their feeding clears pathways for smaller organisms that approach next, each one finding a place within the changing structure. The bones remain, pale and porous, holding within them rich stores of lipids that will sustain life long after the outer form has faded. As years pass, a different community emerges. Bacteria settle into the skeleton and begin to break down those hidden nutrients, releasing compounds that nourish specialized species. Among them are bone-eating worms, slender creatures that anchor themselves into the hard surface and extend feathery plumes into the water. They lack mouths and rely instead on symbiotic microbes within their tissues to process the materials they absorb. Around them grow clusters of mollusks, crustaceans, and other animals adapted specifically to this rare habitat, their life cycles timed to the slow release of sustenance from the bones. This sequence is known as ecological succession, though here it unfolds not in a forest clearing or tidal marsh, but on the deep ocean floor, guided by chemistry and time rather than sunlight. Each stage prepares the conditions for the next, transforming the remains of a single animal into a living community that may persist for decades. Even after most visible traces have disappeared, microscopic life continues its work within the sediment, enriched by the fall, sustaining organisms too small to be seen by distant observers. Such events are scattered and unpredictable, yet they form vital oases across otherwise sparse regions. For creatures adapted to these sites, a whale fall is both shelter and sustenance, a brief abundance in an environment where nourishment is often scarce. The distance between such habitats can be immense, and larvae released from one must drift long intervals before encountering another. Still, the pattern endures, generation after generation, as each descending giant becomes the foundation for new life. In the stillness that follows, only a faint outline may remain, a suggestion in the sediment where the great body once rested. Around that place, the seafloor carries on quietly, its inhabitants continuing their measured routines, while the legacy of the fallen whale persists in the lives it sustained far below the surface of the world. Far from any coastline, there is a region of the Pacific where maps show little more than open blue, an expanse so distant from land that it seems set apart from the rest of the world. This place is known as Point Nemo, an oceanic coordinate located roughly 1,600 miles from the nearest shores of South America, Australia, and Antarctica. No island rises there. No reef interrupts the surface, only uninterrupted water stretching in every direction beyond the reach of sight. Because of that distance, ships seldom pass through these coordinates, and even migratory routes of marine animals rarely converge there. Nutrient levels remain low, carried away by slow circulating currents rather than replenished from continental runoff. Life persists, though sparsely, in forms adapted to open ocean conditions, drifting or swimming through waters that offer little shelter or structure. Above, the sky appears vast and unbroken, and below, the ocean extends downward through its quiet layers, each one undisturbed by nearby shores. This isolation has given the region an unusual role beyond the natural rhythms of sea and sky. Space agencies have chosen this distant location as a resting place for decommissioned spacecraft. When satellites or orbital stations complete their missions and must return to Earth, they are guided toward re-entry paths that lead here, where fragments that survive the descent fall harmlessly into the water. Over time, this practice has earned the area a quiet reputation as a spacecraft graveyard, though the remains rest far beneath the surface, scattered across a seafloor seldom visited. The remoteness of Point Nemo also carries a subtler quality, one felt by those who consider its position on the globe. It represents the furthest possible distance from human habitation, a point where the nearest people are often astronauts passing overhead rather than anyone on land. Such separation is not marked by visible boundaries, yet it exists as a geographic fact, a measure of how wide the ocean can be and how small the continents become when viewed against it. Oceanographers sometimes reflect on this location as a reminder of scale. Even in an age of satellites and constant communication, there remain coordinates where presence is rare and silence uninterrupted. Instruments placed there would record the same gentle motions that occur across countless miles of open water, currents shifting slowly, surface patterns forming and dissolving with the wind. Nothing announces the spot to passing waves, yet its position remains fixed, defined only by distance and the quiet geometry of the Earth. In that remote stretch, the Pacific holds one of its most solitary regions, a place where separation itself becomes the defining feature, and where the vastness of the ocean can be sensed simply by tracing how far away every shore truly lies. Rising from the Pacific floor in long hidden chains are mountains that never break the surface, their slopes ascending through darkness, yet stopping far below the reach of waves. These are seamounts, ancient volcanic peaks formed when molten rock once their foundations cooled and hardened, leaving stone summits suspended in the water column. Some stand taller than the Rockies if measured from base to crest, though their height is concealed entirely beneath the sea, their outlines traced only by sonar and patient mapping. Each seamount begins as fire and pressure beneath the crust, often above regions where magma finds pathways upward through fractures. Over time, repeated eruptions build a cone of basalt and mineral deposits, layer upon layer, until a mountain takes shape. When volcanic activity ceases, currents sculpt the slopes, carrying sediments that settle along ridges and ledges. The peaks may flatten slightly as erosion and chemical processes wear them down, forming plateaus known as guyats, their level tops hinting at distant ages when they may once have approached shallower waters. What makes these submerged mountains remarkable is not only their scale, but their separation. A single seamount can rise thousands of feet above the surrounding plain while remaining isolated from others by vast distances. This solitude shapes the lives that gather upon its flanks. Larvae drifting through the ocean may settle there and grow into populations that remain largely confined to that one elevation of rock. Over generations, such isolation encourages divergence as species adapt specifically to the currents, temperatures, and food supplies unique to that summit. In this way, each seamount becomes a small world, hosting organisms found nowhere else. Explorers who have surveyed these sites often discover communities unlike those of neighboring peaks. Corals attach themselves to the stone, their branches spreading slowly in the steady flow of passing water. Crinoids extend feathery arms into the current, while fish circle the slopes in measured paths. Even microbes vary from one mountain to the next, shaped by subtle differences in chemistry and depth. The pattern resembles a chain of distant islands, though these islands lie entirely below the surface, separated not by air, but by miles of open water. Because they rise into moving currents, seamounts act as gathering points for drifting nutrients and plankton. Water striking their slopes is deflected upward, carrying microscopic food that attracts larger animals. This steady supply sustains complex communities that might otherwise struggle in the surrounding expanse. The mountain itself becomes both structure and provider, its presence altering the flow of the ocean and shaping life around it. Across the Pacific, thousands of these peaks stand in quiet succession, unseen yet immense, their summits crowned with living forms adapted to the solitude of their elevated homes. Each one holds its own assembly of species, its own subtle variations, a collection of hidden heights, by depth that rival the greatest ranges on land, yet remain known only through careful exploration of the waters that conceal them. Beyond the slopes of submerged ranges and far from volcanic ridges, the Pacific floor opens into expanses so level that they resemble a horizon turned sideways. These are the abyssal plains, immense stretches of sediment that extend for thousands of miles with scarcely a rise or hollow to interrupt their continuity. Fine particles have settled here over ages, drifting down from distant waters above until they formed a surface as even as a quiet desert. The ground appears soft and uniform, its texture shaped by the slow accumulation of material too light to sink quickly, yet persistent enough to gather layer upon layer through the passing of centuries. Across these plains, movement unfolds at a pace unlike that of shallower realms. There are no rushing tides or breaking swells, only gradual currents that pass with the patience of breath. The most constant activity is the descent of what oceanographers call marine snow, a gentle fall of organic fragments that drift downward from distant ecosystems. Each particle may be no larger than a grain of dust, composed of microscopic remains, shed cells, or faint traces of life from far above. As they settle, these particles provide nourishment for the creatures that inhabit the plain, forming the foundation of a food web sustained by slow and steady supply. Animals that live here have adapted to this measured rhythm. Many are small, conserving energy as they move across the sediment or burrow within it. Some extend delicate feeding structures into the water just above the surface, collecting the faint rain of nutrients as it arrives. Growth proceeds gradually, reproduction occurs at long intervals, and lifespans often extend far beyond those of related species in more active environments. Even microbial communities follow this unhurried tempo, their chemical processes unfolding at rates that reflect the limited resources available. Because change happens so slowly, the plains preserve traces of events long past. A mark pressed into the sediment may remain visible for years before currents soften its outline. A fallen object can rest undisturbed for generations, becoming part of the landscape through quiet integration rather than decay. In such a setting, time seems to stretch, measured less by motion than by the steady accumulation of tiny transformations. The difference between one moment and the next is subtle, yet over decades the surface itself shifts, reshaped by the patient work of settling particles. These wide regions cover much of the Pacific Basin, forming a vast foundation beneath the more varied terrains described earlier. They hold no towering features, no sudden contrasts, only a continuous plain that extends beyond the reach of ordinary observation. In their stillness lies a different kind of activity, one defined by persistence rather than speed, where life continues in harmony with the slow descent of nourishment and the quiet passage of ages across the level floor of the deep ocean. They resemble delicate sculptures set quietly upon the seafloor, their forms rising in pale lattices that seem too intricate to belong to living beings. These are glass sponges, animals whose bodies are supported not by bone or shell, but by frameworks of silica, the same mineral that composes sand and crystal. Their skeletons are built from countless microscopic spicules fused together into transparent networks, each strand catching faint light and guiding it along its length. Though they appear fragile, These structures possess surprising resilience, shaped by chemistry into designs that endure the immense weight of the ocean above. The construction of such a body unfolds with remarkable patience. A glass sponge grows only a small amount each year, adding thin layers of silica as dissolved minerals drift through the water. This gradual process means that individuals can persist for extraordinary spans of time. Some specimens studied by marine biologists are estimated to be hundreds or even thousands of years old, their earliest growth beginning long before many human civilizations took form. Within their tissues, cells continue their quiet work at a pace matched to the steady conditions around them, unhurried and consistent. Their lineage extends far into the history of life. Fossil evidence shows that ancestors of these sponges inhabited ancient seas hundreds of millions of years ago, long before the first forests spread across land. The basic design has changed little across those vast intervals, suggesting a form already well suited to its environment. Water flows continuously through the sponge's body, entering through small openings and passing along internal channels where microscopic food particles are captured. This constant circulation also supplies oxygen and removes waste, allowing the animal to function without rapid motion or complex organs. Clusters of glass sponges sometimes grow close together, forming reef-like assemblages that provide shelter for other organisms. Small crustaceans and worms move among the branching frameworks, while fish may rest nearby, using the lattice as cover. The sponge itself remains anchored, its presence steady while generations of other creatures come and go. Because growth is so slow, damage to such structures can take centuries to repair, making their survival dependent on the long continuity of stable surroundings. The silica threads within their skeletons possess a subtle property that has drawn scientific attention. They can transmit light along their length, much like fine optical fibers. Researchers have studied this natural ability in hopes of understanding how biological processes shape materials with such precision. Yet within the ocean, the purpose may be simpler, guiding faint illumination across the sponge's surface or helping regulate internal conditions through gentle distribution of light. In their quiet persistence, glass sponges embody a rhythm older than empires, their forms rising grain by grain through centuries of unbroken time. They stand as living archives of the ocean's past, their transparent frameworks holding within them the memory of ages carried silently forward into the present. In the dim reaches of the Pacific, where sunlight never arrives, branching shapes extend from stone ledges and rocky outcrops, forming intricate groves that resemble forests paused in stillness. These are deep water corals, distant relatives of the reef builders found in tropical shallows, yet adapted to colder temperatures and perpetual darkness. Their colors range from pale ivory to muted amber, tones shaped not by light but by the minerals and proteins within their tissues. Each colony begins as a single drifting larva that settles upon a solid surface and slowly builds a skeleton of calcium carbonate, raising delicate branches into the surrounding water. Growth here proceeds with extraordinary restraint. Instead of expanding inches in a season, many of these corals lengthen by only a millimeter or two each year. Layer is added upon layer, a gradual construction guided by steady chemistry rather than rapid change. Because of this pace, some colonies reach ages measured in centuries. Their oldest sections formed long before modern ships first crossed the ocean above them. Scientists studying cross-sections of their skeletons can count fine bands within the structure, much like rings within ancient wood, each band marking a period of formation tied to the slow rhythms of the deep sea environment. Despite their quiet endurance, these corals remain fragile. Their branches are easily broken by contact, and disturbances can take lifetimes to mend. Trawling equipment dragged across the seafloor has, in some regions, damaged formations that required hundreds of years to grow. Even slight shifts in temperature or chemistry may alter their ability to deposit skeleton, since their existence depends on a precise balance of dissolved minerals. Yet, when conditions remain stable, the colonies persist with remarkable steadiness, holding their shapes through generations of surrounding life. Around these coral groves, animals gather as they would in woodland shade. Small fish hover among the branches, using them as refuge from open water. Brittle stars coil their arms along the limbs, while shrimp move between crevices with careful steps. The corals themselves do not hunt actively, yet their presence creates a habitat that supports entire communities. Their branches slow passing currents, allowing food particles to settle, and this gentle trapping of nourishment sustains both the corals and their many companions. Such underwater forests are scattered across slopes and ridges throughout the Pacific Basin, each one shaped by time rather than tide. They stand as living structures built from patience, their forms rising grain by grain in the quiet dark. Though seldom seen, they contribute to the balance of the ocean, offering shelter, feeding grounds, and continuity within environments where growth is measured not in seasons, but in centuries. Across the charts of the Pacific, there are coordinates marked not by reefs or ridges, but by memory, places where vessels once traveled and never returned. Far below those distant routes, the seafloor holds their resting forms. Ships that descended during the conflicts of the 20th century and settled gently into the quiet of the deep. Many of the deepest known wrecks belong to that era, when naval battles unfolded across vast ocean distances and damaged vessels slipped beneath the surface, vanishing from sight within minutes yet remaining intact in the stillness below. As these ships sank, water filled their compartments and guided them downward until they reached the seabed. There they came to rest with surprising grace, hulls upright or slightly inclined, their structures preserved by the cold and stable environment surrounding them. At such depths, temperatures remain low and oxygen levels are limited, slowing the chemical reactions that would otherwise corrode metal. Wood, paint, and even markings can endure for decades, protected by conditions that inhibit decay. The result is a form of natural conservation, as though time itself moves more slowly around them. Explorers seeking these wrecks rely on instruments capable of sensing what human eyes cannot. Sonar systems send pulses of sound toward the ocean floor and measure the echoes that return, revealing shapes hidden in darkness. These acoustic images guide remotely operated vehicles equipped with cameras and lights, which descend along cables to examine the sites in detail. Through their lenses, outlines emerge gradually from shadow, railings traced in pale reflection, decks outlined by fine sediment, the entire vessel resting as it did when it first arrived. Marine life sometimes settles upon these structures, though not in the dense profusion seen in shallower waters. Small organisms attach to the metal surfaces, forming thin coatings that soften edges and blur sharp lines. Fish pass slowly through open passageways, while delicate invertebrates anchor themselves to protruding beams. The ships become part of the surrounding landscape, their materials blending with mineral deposits and drifting particles until they appear less like intrusions and more like extensions of the seafloor itself. Each discovery requires careful navigation and patience. Researchers study historical records, wartime logs, and oceanographic data to estimate where a vessel may have descended. Once a likely area is identified, survey equipment scans the region methodically, tracing patterns across miles of terrain. When an anomaly appears, a shape distinct from natural formations. Vehicles are sent to investigate. In this way, lost ships are found not by chance but through a gradual process of listening, mapping, and descent. Resting in these remote depths, the wrecks remain undisturbed, their forms preserved in quiet suspension between history and geology. They hold within them stories carried across decades, yet they release nothing into the surrounding water except the faint outline of their presence, a reminder that even human creations can become part of the ocean's slow and enduring landscape. Far from any shore, where the surface of the Pacific turns slowly in wide circular motion, drifting objects sometimes gather in a region shaped not by land but by currents. This area is often called the Pacific Garbage Patch, though the name suggests an island that does not exist. What lies there is not a floating continent of debris, but a broad zone where circulating waters guide scattered fragments into a loose convergence. The currents that create this motion form a gyre, a vast rotating system driven by wind patterns and the turning of the earth, its boundaries defined by steady flow rather than visible lines. Within this slow-turning field, buoyant materials carried from distant coasts or passing vessels may linger longer than elsewhere. Plastic, being light and durable, is especially prone to remain near the surface. Sunlight and wave action gradually break larger pieces into smaller ones, producing particles so fine they can drift unnoticed among plankton. These fragments are known as microplastics, and they do not gather in heaps but disperse through the water column, mingling with natural matter until they are nearly indistinguishable without close examination. Scientists studying this region rely on careful sampling rather than distant observation. Research ships tow fine meshed nets that skim the surface, collecting what floats there so it can be analyzed. Instruments measure concentration, composition, and distribution, revealing patterns that shift with currents and seasons. Satellite data helps trace the motion of water masses, allowing researchers to understand how debris travels and where it tends to accumulate. Through these methods, the area becomes less a mythic patch and more a dynamic system, its contents constantly moving within the gyre's gentle rotation. The popular image of a dense raft of trash arose partly from early descriptions that emphasized its remoteness and scale. In reality, a vessel passing through might see little unusual at a glance, since most particles are small or submerged just below the surface. The accumulation is real, yet it is diffuse rather than solid, spread across an expanse of ocean that spans hundreds of thousands of square miles. The effect is subtle, detectable through instruments and sampling rather than spectacle. Marine life encounters this material as it drifts, sometimes ingesting fragments or carrying them unknowingly across distances. Researchers continue to monitor these interactions, seeking to understand how persistent substances move through food webs and habitats. Their work unfolds gradually, mirroring the slow circulation that defines the gyre itself. The region remains a place shaped by motion rather than mass, its reputation formed as much by imagination as by observation. Within that wide, turning field, the Pacific holds a reminder that even the smallest objects can travel far when guided by currents that never cease, their paths traced silently across the open water. Some ocean inhabitants pass through the water almost unseen, their forms so clear that only a faint outline reveals their presence. These are creatures whose bodies have evolved toward transparency, a state achieved not through absence, but through precise arrangement of tissues that bend light rather than reflect it. Among the most delicate examples are certain jelly species, drifting animals composed largely of water, their gelatinous bells and trailing filaments nearly indistinguishable from the surrounding sea. When they move, they do so with gentle contractions, each pulse sending them forward without disturbing the clarity that conceals them. Transparency serves as a form of quiet camouflage. In open water, where shelter is scarce, visibility can invite danger, so bodies that allow light to pass through offer protection without the need for speed or armor. Cells within these organisms contain very few pigments, and their internal structures are arranged in ways that scatter light minimally. Even organs that might otherwise betray their outline are often reduced or repositioned to maintain the illusion of emptiness. Seen from a distance, such animals appear less like solid beings and more like subtle distortions, brief shifts in the pattern of light. This near invisibility also supports a life of careful energy use. Many transparent creatures drift rather than swim continuously, relying on currents to carry them while they wait for food to come within reach. Their tissues require little nourishment to maintain, since they contain few dense materials. A gelatinous body demands less metabolic effort than one built from muscle and bone, allowing these animals to survive in regions where meals arrive unpredictably. When prey does appear, tentacles or delicate appendages extend to capture it, then return to stillness once more. The simplicity of their design reflects a balance between form and environment. Without heavy structures, they remain buoyant with minimal exertion. Without vivid coloration, they merge with the shifting light of the water around them. Even their movements contribute to concealment, slow and measured, so that they do not create sudden contrasts that might draw attention. In this way, their entire existence becomes an exercise in subtlety, each feature aligned with the goal of remaining unnoticed. Observers studying these animals often rely on careful lighting techniques, since ordinary illumination can pass straight through them. Special angles or gentle backlighting reveal their outlines, bringing into view the faint geometry of living glass. Under such conditions, their shapes appear briefly, delicate frameworks suspended in motion before fading again as the light shifts. Drifting through their quiet realm, these transparent beings embody a strategy shaped by restraint rather than display. They neither chase nor flee with urgency, instead allowing the currents to guide them while their nearly invisible forms blend with the water itself, present yet scarcely seen. Sustained by a design that turns simplicity into survival. In the band of ocean, where sunlight fades into perpetual night, predators move with a restraint shaped by scarcity. This region, often called the midnight zone, offers little nourishment and few encounters, so those who hunt there do so with patience rather than speed. Bodies are designed not for long pursuits but for sudden opportunity, and every motion is measured, conserving strength for the rare moment when prey appears within reach. Among these hunters drifts the fang-toothed fish, a compact creature whose appearance seems carved from shadow. Its jaws hold long curved teeth that extend beyond its mouth even when closed, an adaptation that allows it to grasp whatever passes nearby without the need for rapid chase. The fish itself remains relatively small, rarely longer than a human hand, yet its dentition gives it a formidable outline. Muscles along its body are dense, but used sparingly, propelling it only when necessary. For much of its time, it hovers almost motionless, suspended in the water as though waiting for chance to arrive. Not far away in this same dark realm, the gulper eel drifts with a different strategy. Its body tapers into a slender tail, while its head expands into an enormous mouth, capable of opening wide enough to engulf prey larger than itself. The jaws hinge loosely, supported by flexible bones that allow dramatic expansion. Attached beneath the chin is a small luminous organ that glows faintly, drawing curious animals closer. When something approaches, the eel unfurls its mouth in a swift motion, enclosing both water and prey before returning to stillness. The captured meal may be infrequent, yet it is often large enough to sustain the eel for long intervals. Such predators share a common principle of survival. Energy is scarce, so it must be spent with care. Rather than roaming constantly, they rely on ambush or attraction, allowing the environment to bring nourishment to them. Their metabolisms run slowly, their tissues adapted to function with minimal fuel. Even digestion proceeds gradually, extracting as much value as possible from each rare success. In this way, life continues in a place where abundance is unknown, and every resource must be used with quiet efficiency. The forms of these hunters reflect the conditions around them. Eyes may be large to gather faint traces of light, or small if sight is less useful than vibration and scent. Fins are often delicate, shaped for hovering rather than speed. Colors tend toward dark hues that merge with the surrounding water, rendering outlines indistinct. Each trait serves the same purpose: to exist with as little expenditure as possible while remaining ready for the sudden arrival of sustenance. Within this silent stratum, predation unfolds without spectacle. A brief motion, a closing jaw, a return to stillness, and the balance of life continues. The predators drift once more, patient figures in the dark, sustained by a rhythm defined not by pursuit, but by waiting. Beneath the visible floor of the Pacific lies another realm, hidden not by distance, but by layers of sediment that have settled grain upon grain over immense spans of time. Within those compacted layers, far below where any animal burrows, microscopic life persists in quiet obscurity. These inhabitants are bacteria and archaea, organisms so small that millions could rest within a space no wider than a grain of sand. Yet together, they form communities that extend deep into the buried strata beneath the ocean bed. The conditions there are unlike those of open water. Oxygen is scarce or absent. Temperatures shift gradually with depth, and nutrients arrive only through slow chemical diffusion. Still, these microorganisms continue their existence, drawing energy not from sunlight or drifting food, but from reactions between minerals and surrounding fluids. Iron, sulfur, and other elements become part of their metabolism, serving as partners in the exchange of electrons that sustains their cells. This mode of living depends on chemistry rather than light, allowing activity to persist in places where darkness has remained unbroken for ages. Time unfolds differently for such organisms. Their reproduction proceeds at a pace almost beyond ordinary measure. In some buried layers, a single cell may divide only once over hundreds or even thousands of years. Instead of rapid growth, there is endurance, a steady maintenance of life that continues with minimal change. The sediment itself acts as both shelter and archive, protecting these communities from disturbance while recording their presence through faint chemical traces. Scientists studying cores drawn from the seabed have found living cells at depths where pressure is immense and resources are sparse, evidence that life can adapt to conditions once thought too limited to support it. These discoveries have expanded understanding of where living systems might exist. If microorganisms can persist beneath the ocean floor, sustained by mineral reactions and patience, then similar forms might endure in comparable environments beyond Earth. Subsurface regions of other worlds, shielded from harsh surface conditions, could offer settings where chemistry and time provide the ingredients for survival. The idea does not rely on speculation alone, but on observation of life already thriving within the quiet layers below the Pacific. Researchers investigating these buried ecosystems work with careful methods, retrieving slender columns of sediment and examining them under sterile conditions. Each sample reveals gradients of chemistry and population, subtle variations that reflect depth and age. The process requires precision, since the organisms grow so slowly that any disturbance might alter their balance. Through such studies, a portrait emerges of life that is patient beyond ordinary expectation, sustained by processes unfolding at a tempo measured in centuries. Deep beneath the shifting waters above, these unseen communities continue their silent activity. They neither migrate nor change their surroundings quickly, yet their presence demonstrates that vitality can persist in the most concealed environments. In that hidden world below the sea floor, life endures with quiet determination, shaped by mineral, pressure, and time. Beside boiling water, near certain fissures in the Pacific seabed, where mineral-rich water escapes from within the crust, small shapes gather in clusters that shimmer softly in the rising currents. These are vent shrimp, pale crustaceans that live in close association with the hot fluids emerging from the rock. The water issuing from these openings can reach temperatures high enough to scald most marine life, yet the shrimp position themselves along the edges where warmth fades into the surrounding cold. There they remain, moving gently among the currents as though suspended between two worlds. Their bodies reflect the unusual conditions around them. Many lack strong pigmentation, appearing translucent or milky white, since color offers little advantage in an environment untouched by daylight. Their eyes are often reduced, sometimes covered by protective layers of tissue, for sight plays a lesser role than other senses. Instead, they rely on specialized organs that detect temperature and chemical gradients, allowing them to remain within a narrow band where heat and cold balance precisely. A shift of only a few inches can mean the difference between survivable warmth and lethal extremes, so their positioning is guided by constant, subtle adjustment. Along their shells, and within small chambers near their mouthparts, live colonies of bacteria that form a partnership essential to survival. These microbes use dissolved compounds from the vent fluids as a source of energy, converting chemicals into organic material through processes that require no sunlight. The shrimp, in turn, gain nourishment by grazing on the bacteria or absorbing nutrients they produce. This relationship links animal and microorganism into a single functioning system, each sustaining the other in surroundings that would otherwise offer little food. Heat tolerance in these shrimp depends partly on proteins adapted to remain stable at elevated temperatures. Their cellular machinery is structured so that vital molecules do not lose shape when warmed, allowing metabolic reactions to continue even near the edges of the hot flow. At the same time, their tissues must withstand rapid change, since currents can shift unpredictably. The ability to endure such variation reflects generations of gradual adjustment, each refinement shaped by the precise conditions of life beside the vents. Around these clusters, other animals sometimes appear, yet the shrimp often dominate the immediate vicinity of the warm outflow. They gather densely where the chemical supply is strongest, forming living veils that sway in the rising plumes. The scene holds a quiet contrast: cool darkness surrounding a source of heat, delicate bodies thriving beside water that would harm most creatures. Within that narrow margin, life continues with steady rhythm, sustained by partnership and adaptation. In those concealed places, the shrimp maintain their stations, poised between extremes, nourished by unseen reactions, and guided by senses attuned to the faintest change. Their presence reveals how living forms can align themselves with environments shaped by fire beneath the seafloor, enduring where heat and chemistry meet in the hidden depths of the Pacific. Deep within the structure of the Pacific Basin, vast plates of crust remain in slow contact, their edges pressed together along immense boundaries that stretch for thousands of miles. These margins, known as subduction zones, are places where one plate gradually slides beneath another, descending into the mantle with motion so steady it escapes immediate notice. For long intervals, the surfaces remain locked by friction, their movement paused while strain accumulates silently within the rock. Over years and centuries, that strain grows, stored as elastic tension in the bending crust. The plates continue to press, yet their edges hold fast, resisting motion until the force exceeds the strength of the boundary. When that threshold is reached, the locked region releases suddenly. The descending plate shifts downward while the overriding plate springs upward or seaward, and the energy that had gathered invisibly is freed in a rapid pulse. This event is called a megathrust earthquake, among the most powerful natural movements the planet produces. The release does not occur gently. It travels along the boundary in a sweeping rupture, displacing enormous sections of the seafloor in a matter of moments. Where the ocean bottom lifts or drops, the water above must adjust, and that adjustment begins a series of waves that spread outward across the basin. In deep water, these waves may pass unnoticed at the surface, their height modest but their length immense, carrying energy across vast distances with steady speed. Only when they approach shallower coastal regions do they rise and compress, transforming into the surging forms known as tsunamis. The mechanics behind this process lie in the nature of rock itself. Though it appears solid and unyielding, the crust can flex slightly under sustained force, much like a bent branch storing tension before it snaps back. In subduction zones, the bending occurs on a colossal scale, with entire segments of Earth's surface acting as the flexing material. When the release comes, the stored energy radiates outward through both rock and water, sending vibrations through the ground and waves through the sea. Scientists monitor these regions carefully, placing instruments on land and on the seafloor to record subtle movements that precede large events. Seismographs trace faint tremors, pressure sensors detect shifts in the water column, and satellite measurements reveal gradual changes in elevation along coastlines. Each observation contributes to an understanding of how strain accumulates and how it is eventually released. Though the exact timing of such events remains uncertain, the patterns of motion and stress have become clearer through continued study. Across the Pacific, these hidden boundaries continue their patient interaction, drawing plates together, holding them in tension, then letting them move once more. The cycle unfolds over spans far longer than a human lifetime, guided by forces that operate deep within the planet. In that slow and powerful rhythm, the ocean above responds, carrying the imprint of motions that begin far below, where stone shifts and the energy of the earth finds its way into water. Across the rim of the Pacific, a vast curve of islands traces a path that at first glance appears scattered and irregular, yet from a wider view reveals a quiet pattern. These island chains form where the oceanic crust bends and descends beneath neighboring plates, and along those submerged boundaries, molten rock rises through fractures, cooling into new land that lifts slowly above the water. The result is a procession of volcanic arcs, each one marking a place where deep processes shape the surface in silence. Within these arcs, volcanoes do not stand alone but appear in sequences that follow the contours of the plate margins. Some emerge as solitary cones, while others cluster into long island chains stretching across hundreds of miles. Their origins lie far below, where descending crust carries minerals and water into the mantle, lowering the melting point of surrounding rock. Magma forms there and begins its gradual ascent, gathering in chambers before finding passage upward. When it reaches the surface, it solidifies into fresh stone, adding another layer to the evolving landscape. Over long spans of time, this cycle creates and reshapes entire archipelagos. New islands rise as older ones erode, and volcanic peaks that once towered above the sea may sink again as their underlying crust cools and contracts. Coral and sediment can build upon their slopes, softening sharp outlines and forming rings of pale limestone. In this way, land appears and transforms through a balance of uplift and subsidence, each stage guided by the same steady tectonic motion. The deeper significance of this activity lies in what happens beneath the surface. Subduction zones act as pathways of geological recycling, drawing old crust downward, where heat and pressure alter its composition. Elements locked within ancient rock return to molten form, later emerging through volcanic arcs as part of newly created material. This exchange links the surface and interior of the planet in a continuous loop, a slow circulation that reshapes continents and ocean basins alike. Nothing remains fixed, though the pace is so gradual that change becomes visible only across ages. Life adapts to these shifting conditions as landforms evolve. Fresh volcanic soil, rich in minerals, supports the growth of plants once an island cools and stabilizes. Seeds arrive by wind or water, birds carry them across distances, and over generations a barren peak can become covered in vegetation. Along the shorelines, marine habitats establish themselves in tandem with the rising land, forming communities that depend on the contours created by eruptions long past. The arc of islands surrounding the Pacific thus reflects a hidden continuity, a chain shaped by forces operating far below sight. Each peak, each coastline, stands as part of a larger pattern, one that records the patient movement of the Earth's outer shell. Through that ongoing motion, the ocean's boundary is quietly renewed, its rim defined by land born from fire and returned in time to the depths from which it came. Time moves differently in the depths of the Pacific, not by the sweep of shadows or the turning of tides, but by increments so subtle they gather almost unnoticed. In those quiet expanses, live creatures whose lifespans extend far beyond ordinary measure, organisms that persist through centuries as calmly as waves cross the surface above. Among them are deep-water corals, branching animals anchored to stone, their structures rising gradually as minerals accumulate along living tissue. These corals exist at temperatures low enough to slow nearly every process within their bodies. Their metabolism proceeds with deliberate restraint, conserving energy and allowing growth to unfold in fractions of an inch across long intervals. Instead of rapid expansion, they add delicate layers year after year, each one recording a moment of formation within its skeleton. Scientists who examine these structures can read the sequence like a quiet chronicle, tracing variations in chemistry that reflect changing conditions in the surrounding sea. Some specimens studied from the Pacific have been estimated to exceed 2,000 years in age, their earliest growth beginning before many civilizations now known to history had taken shape. Longevity on such a scale depends upon stability. The deep ocean offers an environment where temperature shifts are minimal and disturbances rare, allowing organisms to maintain steady internal rhythms. Without sudden changes to demand quick responses, these animals invest their energy in maintenance rather than motion. Their tissues renew slowly, their cells dividing at rates matched to the calm conditions around them. This unhurried biology reduces wear across time, extending life far beyond what faster environments might allow. Other inhabitants share this pattern. Certain sponges, clams, and fish also exhibit lifespans that span centuries, each adapted to surroundings where resources arrive gradually and competition remains sparse. Their bodies are built not for speed or strength, but for endurance, shaped by the principle that persistence can be more valuable than haste. Growth rings in shells, chemical signatures in bone, and isotopic traces within tissues all reveal the passage of years, offering evidence of lives that continue across generations of more fleeting species. Researchers studying these organisms must approach with care, since disturbance can damage structures that required centuries to form. Sampling is done sparingly, often with remotely guided instruments designed to minimize contact. Through such methods, knowledge accumulates without disrupting the long continuity these animals embody. Each discovery adds to understanding of how life can endure when pace is governed by patience rather than urgency. In the stillness of the deep Pacific, these long-lived creatures remain as quiet witnesses to the passing of ages. While storms sweep the surface and coastlines shift over time, they persist in place, their forms slowly expanding, their existence measured not in seasons, but in centuries. Within their steady presence lies a reminder that life can follow rhythms far older than human memory, continuing with calm persistence in the vast and silent waters below. Reaching the deepest regions of the Pacific requires more than curiosity. It requires machines capable of entering a world that resists intrusion at every level. The descent alone demands engineering of unusual precision, since pressure increases steadily with depth until it presses against metal and glass with relentless force. To withstand such conditions, exploration vehicles must be built from specialized alloys and thick, transparent domes, each component designed to endure compression that would collapse ordinary materials. Constructing vessels of this kind involves years of research and careful testing, and the cost of producing even one can equal that of major scientific facilities on land. Because of these demands, only a small number of deep submersibles exist worldwide. Some carry human occupants within reinforced spheres, while others operate remotely, linked to research ships by long cables or guided through acoustic signals. Each type faces limits. Crewed craft must balance strength with weight, ensuring they can descend safely and still return to the surface. Robotic vehicles depend on power supplies, communication systems, and delicate instruments that must function reliably despite cold and darkness. A single malfunction can end a mission, not through drama but through simple mechanical constraint. Launching such expeditions involves coordination across many fields. Ships must travel long distances to reach remote regions, carrying teams of scientists, engineers, and technicians, along with equipment that fills entire decks. Weather must be considered, currents measured, and navigation planned with precision. Even after arrival, hours of preparation precede a descent, followed by slow progress downward and an equally careful return. Each dive yields only a brief window of observation before time and resources require the ascent to begin. Yet exploration continues, sustained by international collaboration and gradual advances in technology. New materials allow hulls to be lighter and stronger, improved sensors gather clearer data, and autonomous vehicles extend the reach of observation beyond what was once possible. Some machines now glide above the seabed for days, mapping terrain and recording environmental conditions, their movements guided by programmed routes. Others settle gently on the ocean floor to monitor changes over months, sending information upward through acoustic signals that travel across the water. Despite these efforts, vast areas remain unseen. The ocean is immense, and each expedition can examine only a small portion at a time. Detailed maps require repeated passes, careful analysis, and comparison of measurements collected over years. In many places, the seafloor is still known only through broad outlines, its finer contours waiting for future visits. The scale of the environment ensures that discovery proceeds slowly, shaped by patience rather than speed. So the hidden reaches of the Pacific endure in quiet obscurity, not because they are unreachable, but because reaching them demands time, ingenuity, and dedication. With each carefully planned descent, knowledge expands a little further, like light spreading gradually through water, revealing fragments of a world that has long existed beyond ordinary view. Each return from the Pacific carries with it a quiet collection of discoveries, small in appearance yet vast in meaning. Instruments rise from the depths bearing recordings, samples, and images that reveal forms no record had held before. With every carefully plotted descent, scientists encounter organisms whose shapes, textures, and behaviors expand the known catalog of life. Some resemble familiar groups, yet possess unfamiliar structures, while others seem to belong to lineages previously unimagined, their existence known only once light from a lens touches them for the first time. The pattern has repeated so often that it has become an expectation. Year after year, research teams describe new species gathered from trawls, sediment cores, and remote-operated vehicles. Many are minute, visible only through magnification, their bodies constructed with delicate symmetry. Others are larger, drifting or resting in ways that suggest adaptations shaped by conditions unlike those nearer the surface. The discoveries do not arrive as isolated curiosities but as steady additions, each one a reminder that the living world beneath the Pacific remains only partially observed. Adaptations uncovered during these explorations often challenge assumptions about what forms life may take. Some creatures possess tissues that reflect almost no light, rendering them difficult to see, even when illuminated. Others produce structures that amplify faint vibrations, allowing them to sense movement across long distances. Certain species display metabolic pathways that function efficiently despite scarce nourishment, their internal chemistry tuned to operate with remarkable restraint. Each feature represents a solution refined through countless generations, shaped by surroundings that reward subtlety rather than speed. Researchers studying these organisms proceed with patience, documenting every detail that might reveal how such traits developed. Genetic analyses compare newly found species with known relatives, tracing lines of descent across evolutionary time. Chemical studies examine compounds within tissues, uncovering processes that sustain life in environments far removed from ordinary conditions. The work unfolds gradually, since careful verification is needed before a discovery becomes part of scientific understanding. Even so, the accumulation of findings continues, forming a growing record of diversity hidden within the Pacific. This steady emergence of unfamiliar life has altered expectations about exploration itself. Instead of anticipating a final catalog, scientists now recognize that each mission is likely to encounter something unforeseen. The ocean does not yield all its secrets at once, but offers them in fragments, revealed through repeated visits and attentive observation. What once seemed unusual has become a quiet pattern, one that suggests abundance rather than rarity. So, the expeditions continue, vessels crossing open water, instruments descending through darkness, and teams awaiting the moment when data returns to the surface. With each journey, knowledge widens slightly, like a horizon extending as one moves toward it. The Pacific remains vast, its depths still holding forms that have never been seen, and the rhythm of discovery endures, gentle and persistent, carried forward by curiosity and careful search. Night over the Pacific does not begin with darkness, for darkness is already present, far below the surface, long before evening arrives above. As daylight fades across the waves, the depths remain unchanged, holding their steady conditions as they have through uncounted cycles of sunrise and dusk. Down there, pressure rests evenly in every direction, not as a force that moves or strikes, but as a constant presence, firm and unyielding, shaping the forms of all that dwell within it. The water remains cold, not with the sharpness of winter air, but with a stable chill that never lifts. Temperatures hover just above freezing, preserved by the vastness of the surrounding sea. In that stillness, motion slows. Currents drift with gentle persistence, carrying fine particles and dissolved minerals through the dark. Nothing rushes, nothing startles. Even sound travels differently, spreading in long paths that fade gradually into distance, leaving behind a quiet that feels almost tangible. Within this calm environment, life continues at its own unhurried pace. Creatures glide or rest, feed or wait, following rhythms set not by light but by chemistry and current. Some remain anchored to stone, extending delicate structures into the water. Others move in patient arcs, conserving energy as they search for nourishment. Each action is measured, each movement deliberate, as though time itself has softened and stretched. The living world persists, not in haste, but in endurance, sustained by adaptations refined across ages. Above, continents shift through seasons and weather patterns, yet most of the planet lies beneath this immense body of water. The greater portion of Earth rests submerged, its landscapes hidden from view, its processes unfolding without spectacle. Mountains, plains, and valleys extend across the seafloor in quiet continuity, their contours known only through instruments that have traced them piece by careful piece. In that submerged expanse, change occurs slowly, guided by forces that operate beyond ordinary perception. The night sky overhead reflects faintly on the surface, but its light reaches only a short distance downward. Below that thin boundary, the ocean holds its own steady state, indifferent to the turning of the heavens. Pressure remains constant, cold remains constant, silence remains constant. These qualities form the background against which countless forms of life continue their existence, each one part of a vast system that has endured for millions of years. And so the Pacific at night is not a place of stillness alone, but of quiet continuity. Beneath the fading glow of the stars, the great ocean keeps its patient rhythm, its depths sustaining lives unseen, its waters covering the greater share of the world. In that immense and tranquil darkness, Earth itself seems to rest, carried gently within the vast embrace of the sea.